So today we're going to talk about the derivative rules for taking the derivative of an exponential function, a to the x or e to the x. And at the top they have that same definition that we discussed in our notes prior that let us know where the number e comes from. So what we're going to do is just go ahead and fill out this chart. We're going to put the equation that they give us here into our calculator. We're just going to calculate these values, and we're going to try to draw a conclusion. So I've already put this first function in here. There it is. And I'm going to go to the table setup and put it on ask. And then I'm going to go to my table. I've already got some things in here. Let me clear those out. Okay, so I'm just going to type in what they gave us. So 0.1 and then 0.01, 0.001, and 0.0001. All right, so I'm going to write down these values. We have 0.71773, 0.69556, 0.69339, and 0.69317. And then they ask us to find ln of 2. So I'm going to get out of that, go back to my home screen, and just type in ln of 2. And it is 0.693147. All right, we'll come back to this. So I'm going to move on over to the next line. I'm going to go back to y equals and type in e. It's the only change, e to the h minus 1 over h. And then I'm going to go back to my table, and I've already got those same values in there. And so now I'm just going to write these down. So I have 1.0517, 1.005, 1.0005, and 1.0001. And then it asked me to find ln of e. Well, we already know what that one is, but we'll go ahead and type it in. ln of e, whoops, ln of e is 1. Okay. There we go. All right, we have one more. This time they want us to change this to a 3. So I'm going to go back to y equals, change this value to a 3. Then I'm going to look at my table of values again, and there they are. So I have 1.1612, 1.1047, 1.0992, and 1.0987. And they want me to find ln of 3. So go back to my home screen, ln of 3, and I get 1.0986. All right. So now when I look at this chart all filled out, what I'm finding out here is that as h approaches 0, in all of these, h is approaching 0. The closer h gets to 0, the closer this value at the end of my chart gets to the natural log at this number. So this becomes close to this, here 1, here 1.0987. So what we're seeing is that the limit, as whatever this number here is, I'm going to call it a, the limit is a approaches 0 of a to the h minus 1 over h, so it's just this formula. We see that as we get close to 0, that limit is getting close to whatever the natural log of that number is. So when I have f of x equals a to the x, and I want to take the derivative, I'm going to go back to the old derivative rules, to my limit rule. And I'm going to have the limit as h approaches 0 of a to the x plus h minus a to the x over h. This is our definition of the derivative. And so now I have the limit as h approaches 0 of a to the x times, okay, so remember that this addition is actually multiplication. It's a to the x times a to the h. So if I factor out an a to the x, I get a to the h minus 1 over h. Well, we already know that this portion, as I take the limit as h approaches 0, is going to get close to ln of a. This is a number raised to a power not associated with h, so I actually could pull it to the front and I would have a to the x times ln of a. So my derivative equals a to the x ln of a. That's where my derivative rule comes from. Oh, you can see what I was writing. I'm so sorry. Let me go over that one more time. Addition here becomes multiplication. So this is a to the x times a to the h. So I can factor out a to the x, and I get a to the h minus 1. So the limit as h approaches 0 of this portion, we know from right here is ln of a. The a to the x has a, as h approaches 0, has no bearing on that, so it's just a to the x times ln of a. So that's my rule for finding the derivative for an exponential function. So let me give you an example over here. If I have f of x equals 2 to the x power, all this rule says is that if I take the derivative, I'm going to get 2 to the x power times, I don't know why that's a habit, L and N just seem to go together, but I get 2 to the x times the natural log of 2. So if my function were equal to e to the x, then my derivative would be e to the x times ln of e. But what is ln of e? Ln of e is just 1, so I just get e to the x. So it's kind of unusual, but the function e to the x has a derivative of e to the x. So that's what this is telling you. And then if this is raised to an exponent power that is not just x, if it's some other function, then don't forget that you also have to take the derivative of that function as well. So before we get started on these, I'm going to give you an example of that last little rule there. If my function is e to the 3x power, for example, then the rule says that the derivative would be e to the 3x power times the derivative of this function, which is 3, or just 3e to the 3x power. So pretty simple to use. Just wanted to show you an example before we do these examples. So here we go. All right, so our first function, we have 2 times 3 to the x plus 5e to the x. Remember that this 2 and this 5 are just constants in the front, just like if we had 2 sine x, we would get 2 cosine x as the derivative. That 2 just kind of tags along. So whenever I find my derivative, it's going to be 2 times the derivative of 3 to the x power. And the derivative of 3 to the x, we just went over this, is 3 to the x ln of 3. Plus, and then we have that constant 5 times the derivative of e to the x, which is e to the x. So that's about all I can do. I guess I could put the 2 ln of 3 together times 3 to the x. It really doesn't matter. Plus 5e to the x. All right. For this second one, our derivative of e to the u is e to the u. So e to the tangent x power times the derivative of the exponent, which in this case is secant squared x. That's pretty much it. That's all we can do. For number 3, we're going to need to use the product rule. We have two separate functions here. So our derivative, first derivative second, plus second derivative of the first. So first times the derivative of e to the 2x, which is going to be e to the 2x, times the derivative of the exponent, which is 2. So first derivative of the second plus the second times the derivative of x, which is 1. So we have 2x e to the 2x plus e to the 2x. So we could factor out an e to the 2x, since they have that in common, and have 2x plus 1. That would probably be easier to solve if we had to set that equal to 0 when it's factored out. Okay, then number 4. Looks like we need to use quotient rule. So my derivative, I'm going to have the bottom times the derivative of the top, so e to the 3x times 3, minus the top, e to the 3x, times the derivative of the bottom, and the derivative of 1 is gone, and so the derivative of e to the x is just e to the x all over the bottom squared. Alright, so we are going to distribute up here on the top. We have 3e to the 3x, so I'm just going to distribute 3e to the 3x times both of those. We would have 3e to the 3x plus, and then e to the x times e to the 3x. When you multiply, you add the exponent, so that's going to be 4x. So I get 3e to the 4x power minus, and then again we're multiplying, so we add the exponents, e to the 4x. All right, these have the same term here, so it's just 3 minus understood 1. So we have 3e to the 3x plus 2e to the 4x over 1 plus e to the x squared. Now, if you wanted to take that a little bit further, I guess we could do some factoring, but I think I'm just going to leave it there for now. And then on this last example, it looks like we might have to do some implicit differentiation because we've got an xy as an exponent here. So for our derivative of e to the xy, we get e to the xy times the derivative of the exponent. And this is where we're going to need some implicit differentiation, because we're going to have to do first derivative of the second plus second derivative of the first, and these are with respect to x. So we're going to have x, the first, times the derivative of y, which is 1 dy dx, plus the second, which is y, times the derivative of the first, which is just 1. All right, so the derivative of e to the y, or e to the xy, is e to the xy times the derivative of the exponent. All right, plus the derivative of x squared, which is 2x, and then minus the derivative of 2y, which is 2y dy dx, equals 0. All right, so we're going to go ahead and distribute here. We have x e to the xy dy dx plus y e to the xy plus 2x minus 2y dy dx equals 0. I need to put my dy dx's on the same side, so I think I'll just leave those on the left. Minus 2y dy dx, and move these other two over here to the other side. So minus 2x minus y e to the xy. All right, then we factor out the dy dx. So x e to the xy minus 2y. And then we divide. And so this is our derivative. So this is a pretty good set of examples because it not only has us go over our new rules for derivative of exponential functions, but it applies them with implicit differentiation, the quotient rule, the product rule, trig rules. So pretty good practice of all of our rules here.